Okay, thank you very much for the opportunity to talk about this work. The primary goal is to get you out much before 12:30 for lunch. And the secondary goal, of course, is to explain the work that we've done. So I'm going to talk about, am I too quiet? Is it? Oh, I'm good, okay. I'm going to talk about Hamm-Grams, so mining frequent regular expressions of bytes work I've done with Edward and Jim, with many thanks to RJ, Richard, and Ryan. Okay, so I'll first introduce the motivation for this work, talk about a high-level overview of how the algorithm works, talk about our locality-sensitive hash, talk about how we will build regexes inside of the hash buckets, and talk about results. Okay, so suppose that we have large corpora of static files, for example, binary files, for example, Windows portable executable files, and we'd like machine learning algorithms which can infer some meaningful features from these corpora. So these could be static byte-based features, such as n-grams, which we've used a lot. And we want these features to be predictive of whether a file is malicious or benign, or maybe the family it belongs to, or something. Hopefully this is. So like I said, we have baseline models that compute n-grams, but n-grams are brittle to a change in any one of those bytes. So it would be cool if we had something that could infer something which looks more like a regex than just a static sequence of bytes of length n. Okay, so this is a motivating example. These three assembly instructions are equivalent to a 5-gram in hex 5529D289E5. If we replace the second instruction to something which is operationally equivalent, that 5-gram will now become 5531D289E5. Okay, so those two 5 grams are different. They represent the same instruction, basically. So what if we could find 55 wildcard D289E5? That would be cool. So that's what we're going to try to do. And many assembly instructions have these kind of examples, fixed length equivalent counterparts, and byte representation. Okay, keep that example in the forefront of your mind, because now I'm going to pretend that I'm doing it on English letters, just because I don't want to stumble over explaining how the algorithm works. So I'm going to pretend that this whole thing works on lowercase English letters, hashing and all that. But please always remember this example that I just discussed, that it's actually operating on the 256 bytes. Okay, so if you're familiar with the kilogram algorithm from Edward, roughly 2018, this whole idea will be familiar. So we have our corpus, and we're going to roll a hash function over the corpus and over each n-gram in the corpus. So for example, these are 6 grams of English letters. Again, pretend they're bytes. Okay, so we're going to roll this rolling hash over all the n-grams in every single file in the corpus, and bucket them into buckets, because there are too many n-grams to count them all at the first stage. So we first have to do like a coarse counting by putting them in buckets. So we're going to have collisions if we have a hash function. And if we make our hash function locality sensitive, then what we hope to have is, if you look in the third bucket above count 2, where we have the 6 grams, random and ransom. Those differ by 1 character. They have Hamming distance 1, so ideally those would collide into the same bucket. Okay. And again, at this first stage, the idea is just that we're counting the bucket, counting the hashes themselves. Okay. So is it okay if I step down here? Yeah, okay. Please don't look at me, look at the slide anyway. So for each token, just assign a complex number that has radius 1. So you're going to put it on the unit sphere in the complex complex plane. So for visualization purposes, I've just taken two English letters, A and B, A in blue, B in green. I've given them a random complex number which sits on the unit circle. Okay, so now imagine again, you're doing that for all of the 256 bytes, actually, not just A and B. Okay, so we want our hash to be locality sensitive to the Hamming distance, not just something like the Jacquard distance, which would be permutation invariant to the ordering of the sequence. So we're going to also encode position with exactly the same trick, roughly speaking. So we're just going to take a random complex number, I call it phi, and we're going to fill a vector with powers of that number phi. So 1 and then phi squared and so on, up until we have a vector of length n. So in this example, if we're going to do 6 grams, that would be a vector where we end at phi to the power 5. Those just wind around the unit circle. Okay, why the hell? Why are we doing this? Okay, so the whole point is this quantity now where you take the dot product between that vector w, which is filled with powers of phi, and the encoding of the sequence x, you take that dot product, it's useful for two reasons. So the first reason is that n-grams with small Hamming distance will tend to be closer together in the plane. So we've computed, if you using the numbers on the previous slide, the sequence AAA, BAB, its like complex number encoding is in blue. The sequence AAA, AAB is in green. Those have Hamming distance 1 again. So you see that those lie close together. The sequence BBB-ABA, which differs by Hamming distance 6 to the first, is on the other side of the plane. It's farther away. Okay, so if this doesn't do a good job of visualizing, just imagine you're adding vectors of size 1 tip to tail in the plane. And every time you have a different token multiplied by its special number for where it falls in that sequence, you have to subtract that vector and put in a new one. And that's why you're limited how far you can be from where you started. So anyway, to make a bit, you can just take the real part, or basically which half of the plane do you fall in as a binary hash code. You could do this whole process m independent times, with m different random choices of all these numbers. Okay, so what the plot in the right is showing is that if you make random n-grams, the probability of having a collision between a pair of them depends on the Hamming distance to the pair, which is exactly what we want. We want things with smaller Hamming distance to have a higher collision probability, and things with large Hamming distance, very dissimilar sequences, to collide much less often. So if we make random 10 grams of 256 bytes, and we have 10 bits in our hash, basically we do the whole complex number business 10 times independently. What you get is the plot on the right, where the probability of a collision decays very quickly with Hamming distance, which is, Hamming distance is h sub d. I've just scaled it by n, which is 10 in this case, just to make it easy to look at. The second reason that this is useful is our hash function has to be very, very fast, because we have to hash we have to hash every single n-gram in every single file. We're not just hashing the file once. So when you look at this inner product W transpose X, if W has size n and X has size n, that looks like it's order n to calculate. But the way it's designed, it has an order 1 update rule. So you can do the algebra, or maybe it's more fun to just look at the picture. in the right-hand side. So the sequence AAABAB, its like complex encoding is shown in the blue dot. And pretend that we've just computed our hash inside some corpus of, AAABAB. And now we slide the window one token over, and now we need to compute the next window, AABAB. Oh, I'm sorry, read that wrong. AABABB. Okay, so that's shown in green. We don't have to compute that hash like afresh. We're going to use the previous hash we computed, subtract off the first token, which rolls out of the window, multiply it by the inverse of our special number phi, and then add something basically just to say we have to put that new vector on the end. Okay, so that's why this is rolling. That's why it's fast. And that's how we can hash every single n-gram in every single file in our corpus. So again, we're counting the top k hashes. In our we're going to take another pass after we say, what are the most popular hashes? We're going to ask, what are the actual n-grams that fall into these hash buckets? And we've saved those, so inside of each bucket now, we have n-grams that have small Hamming distance. So now we want to build a regex out of them by clustering them together. So the way that we do this right now is we use agglomerative clustering up to like a kind of budget where you say like, you can have a regex with 2 wildcards, but no more, that type of thing. So again, in this example, if you look at this pool at the left of words of 6 grams, the 6 grams random and ransom have Hamming distance 1. Those are the closest pair, cluster them together, and put a wild card where they differ. So you have RAN, wild, OM. Okay, now do it again. Now we have the closest pair is shiver and silver. Those have Hamming distance 2. Okay, S wild, wild, VER is our new Hamm-Gram, etc. until you finish and you have no pairs which can be merged without exceeding your budget. Sorry, back. Okay. Now we're going to put all the regexes in a prefix tree and take another pass over the corpus to count matches, because again, we want our features to be the top k most popular regexes. So this is really easy. This is exactly what a prefix tree is for. So if you're walking the corpus and you see the 6 gram solver, SOLVER, okay, that's a match to your prefix tree because I have S wild, VER. The reason we have to take this third pass is because if you remember, or I'll remind you, the Hamm-Gram S wild, VER was built of 2 different n-grams, which were silver and shiver, not solver. So we have to count solver then in this third pass once we have the regex. Okay, so let me explain this wall of text, the key to it. So N denotes the size of an n-gram, H denotes the size of a Hamm-Gram, how many tokens or wild are in the Hamm-Gram. If you see 2 question mark or 4 question mark, that means the budget's either 2 wildcard budget or 4 wildcard budget. So we featurized the Ember 2018 train corpus, both with this new Hamming-Gram way and the kilogram way with a Robin Carp hash. We took those top 10,000 features in either case, and we either trained logistic regression with lasso regularization or light GBM model for n-grams and Hamm-Grams of size 8 and 16. And then we computed the area under the ROC curve on Ember 2018 test on a small subset of the SOFO-Sorel data set, which is a little bit newer than Ember 2018 test. and also on virus total that are group collected. I just took files, Windows PE files from October 2023. So first, I'll just discuss the light GBM comparison. So in this case, the N-grams perform, the N-grams and the Hamm-Grams tie on Ember test, and the N-grams generalize better to the small SOFO subset and the more recent virus total data set. If we use the logistic regression with Lasso, the Hamm-Grams of size 8 with 2 wildcards perform better on Ember test and also generalize better on the SOFO subset and on virus total from October. Okay, next steps, we need to probably need to create a training data set that has larger, larger amounts of near duplicates, because that's really what we're looking for to try and mine from the corpus with this Hamm-Gram algorithm, and further optimizations so that we can scale to even larger data sets and larger numbers of the top K hashes. Okay, thank you.
Excellent. Great talk. Hiram, you have a question?
Yeah, first, love the talk and love the name, Hamm-Gram. It's brilliant. Just if you could, I can't remember the computational complexity of Robin Carp, but what is the difference? Like,
It's also rolling.
but it's rolling, but like how many ops per?
Oh,
Yeah, I'm just here like
this is more expensive because I
with
have to do like
2 more
complex-
multiplications, you get locality. Is that the idea?
Hmm?
Like with two more multiplications, you now get LHS
Oh, you mean the complex?
compared to Robin Carp. Yeah,
I think
Yeah.
so. Yeah,
that's amazing.
it's slower, but yeah.
Additional questions?
Hey, thanks for the talk. In your motivational example, you had these 3 assembly instructions, and I was wondering if we keep the instructions the same and we just change the registers, like the N-gram will not match, right? Is there any way to go around this?
That's a good question for someone who knows more about this than I do. So I don't know the answer to that. Yeah, but it's a very good question. I'll have to ask Edward or Richard that.
All right, we got one from the Slack. Very interesting idea. Seems that an optimal choice of K is essential for the algorithm to work. For example, large K would mean many wildcards. Do you have any thoughts on that?
Yeah, so I think they mean the number of wildcards, which I didn't give a name. So I'll assume that's what they're talking about. Indeed, the number of wildcard or like the budget is a parameter that right now our approach will be just to treat it as a hyperparameter in it once we can scale.
Excellent. More questions? All right, cool. Well, closed out early, and I guess it's time for lunch now. Remember your tickets and follow the herd to the food trucks.